Welcome to welcome to the 70th lecture. We are studying today. We will start studying transient analysis of circuits. Before this, we have been studying three-phase circuits. In this lecture and in the upcoming lectures till the end term examination, we will be studying transient analysis of circuits. Transient means the response of the circuit when we quickly apply an input source or we quickly remove a voltage or current source. So the response of the circuit by quickly applying or quickly removing a source is called the transient analysis, right? But before we start transient analysis, we will study some basics of capacitors and inductors. In this lecture, we will study some basics of capacitors. A capacitor, a simple two parallel plates capacitor consists of two plates where the current we know is, we have studied in elementary classes that current can be written as the rate of change of the charge or anything, right? Even for a resistor or for anything, any conducting material, I is the rate of change of charges. So there is that dielectric is the medium that is between these two plates. It can be air or anything else, right? So what we're going to study today is that I can be written as the rate of change of charge, and Q, charge, can also be written as CV. This we have already studied in elementary classes. Q is the charge is C. C is the capacitance in farads. V is the voltage drop across the capacitor. V. Right. So I can be written as C times time derivative of V, because we have replaced this Q with CV, C times V. So C is not the function of time, it's a constant quantity. Therefore, we can write C out of the derivative term, and this time derivative of V. This V is V of t, because V is the function of t. So if V is the function of t, I must also be the function of t, and it is written like this: I of t is C times time derivative of the voltage. So this V is the voltage drop across this capacitor, V sub C, and this I is also I sub C, the current flowing through capacitor. So if there is a change in voltage, why we are studying this? Because we are going to study the transient behavior of capacitors. So when we'll be changing V of t, suddenly in our upcoming lectures, we'll be changing V of t suddenly, quickly. So we want to study the impact of current, that is C times the time derivative of the voltage drop across capacitor. Right. So this can be written other way around. We can, this formula computes I of t given V of t. So what if I of t is given and we're going to compute V of t? So that's simple. We'll integrate on both sides, integrate with respect to t on both sides, on the left hand side and on the right hand side of the equation. Minus infinity to t are the limits. So this C is this C. The time derivative of V of t, this dt cancels with this t. So, and this derivative term V of t, C times. So we have integral of V of t, which is V of t. Right? We have integral over integral dx is x. Right? So we have integral dx is x. So in the same way, this is tc. If we take c out of this integral, so integrating dv of t from minus infinity gives V of t. Right. So on the left hand side of the equation, this is written as such. Right. And this integral on the right hand side of the equation can be broken up from minus infinity to t. So we can decide a time, maybe time 0, or time in general time t naught. So if we have this timeline from minus infinity to t naught sometime, it can be 0 or it can be any other time, and this is the t we want to compute. So this integral can be written in terms of can be broken up in two parts, from minus infinity to t naught, and then from t naught to t, like this. So this v of t can be written as this much. Minus infinity to t naught is the capacitor pre-charged. So this is the voltage that is already present on the capacitor before we have applied our input voltage. Right. So this is the voltage already present on capacitor. Right. So P can be written as V of t times I of t. I of t is, we already know, I of t is C times time derivative of V of t. So energy, we know energy is the integral of the power. So if we integrate this power over minus infinity to t, this is, and we put this expression of V of t right here, this becomes V of t C d by dt of V of t, and then this t of t. This t of t is this one, dt, sorry, dt. So dt cancels with dt, and V of t, the c comes out because it's not a function of t, it's a constant term. So V of t times dvt, dv of t. So integrating V of t with t of t, it's exactly like integrating x dx, and we know that this integral gives us integral x dx gives us x squared divided by 2. So in the same way, if replacing this v of t with x for your own convenience, and then we can put it back. So this is v squared of t over 2. This is the energy that is stored in capacitor. We can write this same term, we can write 1 by 2 times c times v squared, and then we can put these limits in, v squared t minus v squared of minus infinity. So assuming that it wasn't initially charged, then the expression for energy stored in the capacitor is 1 by 2 times c times v squared of t. Right. These are some simple terms about, simple expressions about the current. In this lecture, we have studied about current in a capacitor when we suddenly change input voltage, or when the current, and then we can rewrite this expression to find v of t given I of t, that is computed using this integral term, and then the expressions for power and energy stored in the capacitor. Right, we will keep on studying more about transient analysis of circuits in our upcoming lectures. Thank you.